Today's topic will be on kinetic theory of gases and gas law. Gas law. Now, before we consider gas law, let's look at kinetic theory of gases. You see that matter is made up of atom, molecules, and ions. So we have the particulate nature of matter, and we also have the state of matter, where we have solid, liquid, and gases. But for you to understand matter better, or the state of matter better, then we have to look at the particles that make up solid, liquid, and gases. The behavior of the three states of matter depends on how the molecules within these states of matter behave. If we take solids, for instance, we normally say that it is hard to compress solids. It's because of the arrangement of molecules within solids. They are closely packed, so they don't have enough space to occupy when you compress solids, which is different in the case of gases, where they are distant apart and we have enough spaces between the molecules of gases. So they can easily be compressed when it comes to gases. So for us to understand gas law, then we have to begin with the kinetic theory of matter, where we talk about the particulate nature of matter. Now, the behavior of gases depends on the variation in the physical state of matter. For us to understand gases very well, then we have to understand the changes in its physical state. We have pressure, volume, and temperature. So these are the state variables, which is also known as state coordinates for gases: pressure, volume, and temperature. So what effect do these physical states have on the behavior of gases? So gas law simply explains the behavior of gases when pressure, volume, and temperature changes. Don't forget, I told you the behavior of gases depends on its physical state. In other words, for us to observe the behavior of gases, then we have to consider the effect of the changes in pressure, volume, and temperature. And for this topic, we are going to consider only three laws. The first one is Boyle's law. The second one is Charles' law. And the third one is pressure law. Now let's begin with Boyle's law. Boyle's law. For us to begin with this, we have to consider two different containers. Let's take this to be container A, and let's take this to be container B. If you compare the sizes of these two containers, one is bigger than the other. Let's occupy the containers with the same number of molecules. So we have 5 molecules in container A, then 5 molecules in container B. The amount of space occupied by these molecules won't be the same as the amount of space occupied by the molecules in container B, because these containers have different sizes. Now, let's maintain the temperature of the molecules or the gas constant. You see that the gas has its initial temperature. So the molecules within the gas have some form of energy for them to move. But don't forget, in gases, the force there is weak. So the molecules are already distant apart. So they can easily move when they are heated. So when you take container A, since it's having a smaller size, the molecules within the gas do not cover longer distances before they can collide with the walls of the container. They only cover short distance. So in container A, the molecules are able to collide more frequently in the container. And the more they collide with the walls of the container, the more pressure is being generated in container A. So the generation of pressure in this container is due to the collision between the walls of the container and the molecules. Now let's come to container B. This one is having a bigger size. So the molecules will take a longer distance before they can collide with the walls of the container. So the collision between the walls of the container and the molecules in this container is less as compared to this. So the pressure generated in container B will be smaller than the pressure generated in container what? A. But if you look at the volume of these two containers, this one is smaller than what? This. And the pressure generated here is greater than what? That. So this tells us that there is an inverse relationship between pressure and volume. The greater the volume, the smaller the pressure generated. Then the smaller the volume, the higher the pressure generated. So this will lead us to Boyle's what? Law. So Boyle's law states that the pressure of a fixed mass of gas is inversely proportional to its volume, provided temperature remains constant. So here we've kept the temperature constant, and we are observing the variation between pressure and what? Volume. So from this scenario, pressure is inversely proportional to volume. The smaller the volume, the greater the pressure generated. And the greater the volume, the smaller the pressure generated. So back to Boyle's law once again. It states that the pressure of a fixed mass of gas is inversely proportional to the volume of the gas when temperature remains constant. So mathematically, we can write this expression. We have pressure being inversely proportional to volume. So P is inversely proportional to volume. And in mathematics, this symbol is called the symbol of proportionality. And we don't always work with this symbol. So we have to introduce equal to and a constant K. We're going to have P equals constant K, all on what? V. So we are going to have, let's make the constant K the subject. So we are going to have PV, we cross multiply, equals the constant K. Now, let's check the changes in pressure and volume. Let's assume the pressure has increased, or the pressure has changed to a new pressure, and the volume too has also what? Changed. So we are going to have P1 V1 equals P2 V2. So this is the formula under Boyle's law. Okay, now let's look at a graph plotted between pressure and volume. So we have pressure being plotted against volume. From Boyle's law, or from the kinetic theory of matter, we understood that as volume decreases, the pressure has to increase. In other words, when volume increases, pressure will decrease. So pressure decreases exponentially with volume. So this is the graph that shows the variation between pressure and volume. Or we can also plot pressure against the inverse of the volume, so 1 on V. And this will yield a straight line. So these are the two graphs under Boyle's law. Now let's move to Charles' law. Pause. Now let's move to Charles' law. So let's consider this container with the same number of molecules. At this time, we are going to keep pressure constant. So we are going to make sure that the pressure generated is not changing. That's why we are considering only one container. So at this time, when we heat up this container, or when we heat up the gas, the molecules within the gas will gain enough energy to collide with the walls of the container to increase or to expand the container. So here we can say that the higher the temperature of the molecules of the gas, the higher the volume. So there is a direct relationship between volume of the molecules of the gas and temperature, and this will lead us to Charles' law. And Charles' law states that the volume of a fixed mass of gas is directly proportional to its absolute temperature when pressure remains constant. I'm repeating, Charles' law states that the volume of a fixed mass of gas is directly proportional to its absolute temperature when pressure remains constant. The absolute temperature there tells us that temperature should be measured in Kelvin, not in degrees Celsius. So if they give you a question where the temperature is in degrees Celsius, it's up to you to convert it to Kelvin. That's why we are using absolute temperature. And from this Charles' law, mathematically, we can write V is directly proportional to temperature. So we introduce equal to and a constant K. Then the absolute temperature will follow. Now let's make constant K the subject. So we are going to have V over T equals constant K. Now, let's assume we have changes in the volume and temperature. So we are going to have V1 on T1 equals V2 on T2. So this is the formula under Charles' law. Now let's look at the graphical representation of volume and what? Temperature. How the volume varies with temperature graphically. So we are going to plot volume against temperature, where this temperature is absolute temperature and the unit will be in Kelvin. But from Charles' law and the kinetic theory, we found out that temperature varies directly with volume. So as volume increases, temperature will increase. In other words, when temperature decreases, the volume of the molecules of the gas has to decrease. So there is a direct relationship. So this will give us the graphical representation as we plot volume against temperature. Okay, now let's assume we are plotting the temperature in terms of degrees Celsius. In terms of degree Celsius. Don't forget, if you want to change degrees Celsius to Kelvin, we add up 273. And if you want to change degrees Celsius to Kelvin to degrees Celsius, we subtract 273. So let's have negative 273 here, negative 273, and this will be 0. So this will give us the graphical representation of volume against temperature. So when we plot volume against temperature in degrees Celsius, this will be the graphical representation. But if you plot volume against temperature in Kelvin, that will be the graph. Now let's move to pressure law. Pressure law. So far we've considered variation between pressure and pressure and volume and temperature. It's left with the variation between pressure and temperature. So yes, we are going to consider a container with 5 number of molecules. We are keeping the volume constant where the temperature varies. When we increase the temperature of the molecules of the gas, they will have enough energy and they can collide more frequently against the walls of the container to generate or to increase the pressure of the gas there. So we can say that pressure increases as temperature increases, or pressure decreases as temperature decreases. So this tells us that we have direct relationship between pressure and temperature as we obtain for Charles' law. So this is how we go about pressure law. It states that the pressure of a fixed mass of gas is directly proportional to its absolute temperature when volume remains constant. I'm repeating, pressure law states that the pressure of a fixed mass of gas is directly proportional to its absolute temperature when volume remains constant. So mathematically, we are going to have P being proportional to temperature T. So we introduce equal to a constant K, then the absolute temperature follows. Let's make constant K the start. We're going to have P on T equals constant K. Now let's assume we have changes in pressure and temperature. So we are going to have P1 on T1 equals P2 on T2. So this is the formula behind pressure law. Did for Boyle's law and Charles' law. Let's look at a graph when we plot pressure against temperature. So we have pressure and temperature. This temperature is absolute temperature, so the unit will be in Kelvin. And there is a direct relationship. So we are going to have a linear graph. As pressure increases, the absolute temperature has to increase. When pressure decreases, absolute temperature also have to decrease. We can also plot pressure against temperature in degrees Celsius. But if we want to change degrees Celsius to Kelvin, we add 273. If we want to change Kelvin to degrees Celsius, we subtract 273, so we have negative 273 degrees Celsius. This is 0 degrees Celsius. So this will be the graphical representation when pressure is plotted against temperature. It will yield a linear graph. Okay, good. Now, in a nutshell, from Boyle's law, when volume increases, we expect pressure to decrease when temperature is kept constant. Under Charles' law, when temperature increases, we expect volume to increase as well when pressure is kept constant. And under pressure law, an increasing temperature will result in increasing pressure when the volume is kept constant. So all these come together to form gas law. When we started, I told you gas law explains the behavior of gas when there is changes in pressure, volume, and temperature. So we are going to combine all the 3 equations that we obtain for the individual laws. Under Boyle's law, we had PV to be equal to constant K. That is for Boyle's law. Then under Charles' law, we also had V on T to be equal to constant K. And under pressure law, we had P on T to be equal to constant K. So when we combine all these 3 equations, we are going to have PV on T equals constant K. So if there is a change in all these 3 parameters, where the pressure changes to a new pressure, the volume changes to a new volume, and the temperature changes to a new temperature, we are going to have PV P1 V1 on T1 equals P2 V2 on T2. So this will give us gas what? Equation. But we are saying that PV on T equals what? Constant. Where this constant is called universal gas constant. So now we are going to have PV on T to be equal to R. This R represents the constant which is known as universal gas constant. So for n number of moles, the formula now reduces to PV on T equals nR. So when we cross multiply, we are going to have PV equals nRT. So this is the formula for ideal gas. We call it equation of state of ideal gas or equation of state of perfect gas. So this comes together to give us gas law, that is the equation of state of ideal gas or perfect gas. P represents pressure, V represents volume, N is number of moles, R is universal gas constant, and T is absolute temperature, where measurements are taken in Kelvin, not in degrees Celsius. We've obtained the equation of state of ideal gas or perfect gas as PV equals nRT, where P is pressure, V is volume, N is number of moles, R is universal gas constant, and T is absolute temperature. But number of moles, N, equals number of molecules, the number of molecules in the gas, number of molecules in the gas on Avogadro's number. So you are going to have N equals number of molecules in the gas, that's capital N, on Avogadro's number of molecules, so Na. So in place of number of moles N, we can substitute number of molecules in the gas on Avogadro's number or Avogadro's constant. So you are going to have PV to be equal to capital N on N subscript A, then RT. But we also know that R on Na, that is universal gas constant on the Avogadro's number, will give you Boltzmann's constant. Which is what? K. So in place of R on Na, we are going to substitute capital K, where capital K represents Boltzmann's constant. So we have PV equals capital N, that's the number of molecules in the gas. In place of R on Na, we substitute Boltzmann's constant K. So followed by K, then absolute temperature. So this is the other way of writing an ideal gas equation, where N is number of molecules in the gas, capital K is Boltzmann's constant, T is absolute temperature. So we have R to be universal gas constant, which is 8.3145 joules per mole per Kelvin, and Avogadro's number to be 6.0. They are all constants, so it will be provided in the question. 22 times 10 to the power 28 molecules per mole. And K, that is Boltzmann's constant. So this is the equation of state of ideal gas or perfect gas, which can also be written in this form, where we have number of molecules in the gas, Avogadro's number, or we can also write it in this form, where we have Boltzmann's constant, then the number of molecules in the gas. Now let's look at the kinetic assumptions of ideal gas. From kinetic theory of matter, if we consider gas, we have molecules within it, and we have a large number of molecules within a gas, and these molecules are in random motion, and for that matter they collide with one another and also against the walls of the container, and there is a weak intermolecular force between these gases. So this leads us to the kinetic theory or assumption of gas. The first one is this: gas is made up of large number of molecules. 2. The molecules of gas are in constant random motion. 3. The volume of the molecules of the gas as compared to the volume of the container in which the gas is occupying is negligible. 4. The force of attraction between the molecules of the gas is negligible. 5. The collision between the molecules of the gas and also against the walls of the container is a perfect elastic collision. And since the perfect elastic collision, then the sixth assumption will be this: the time of collision between the molecules of the gas and also against the walls of the container is also negligible. Then 7. The total energy of the gas depends on the kinetic energy of the molecules. Then 8. The kinetic energy of the molecules depends only on the temperature of the gas. So these are the kinetic theory or assumption of gas. Okay, now let's look at rare gases. So we have ideal gas and also have rare gas. Ideal gas obeys gas law and kinetic theory or assumption of gases. But rare gases do not obey gas law, neither do they obey the kinetic theory of gas. And rare gases give, this is the equation of state of rare gas. We have P plus A on V squared into bracket V minus B equals nRT. So this is the equation of state of a rare gas, and it is also known as the van der Waals equation of rare gas. Van der Waals equation of rare gas. When I told you rare gas does not obey kinetic theory of gases, and under kinetic theory of gas we said that the volume of the molecules of the gas is negligible as compared to the volume of the container, and the force of attraction to it is negligible. But in the case of rare gases, that is different. Rare gas, in the case of rare gases, this equation is based on van der Waals assumption of gases. And then the first assumption, van der Waals says that the volume of the molecules of the gas as compared to the volume of the container in which the gas is occupying can never be neglected. So here we have to consider the volume of the molecules of the gas, because the molecules have a definite shape and they have an appreciable size. So he said that the volume of the molecules of the gas should be B, and the volume of the container is V. So for you to know the exact space or volume that is being occupied by the molecules of the gas, then it has to be the volume of the container in which the gas is occupying minus the volume of the molecules of the gas. So we have V minus what? B. Then 2. The force of attraction, which was neglected under kinetic theory of gas. When it comes to van der Waals assumption where rare gas is based, that force of attraction shouldn't be neglected. And if this force of attraction is not neglected, then the molecules of the gas are not being opposed. So they can, if this force of attraction is not neglected, then it means the molecules of the gas are attracted to one another, so they can't move frequently and at a faster rate to collide against the walls of the container. So the pressure generated for rare gases is less as compared to the pressure generated for ideal what? Gas. So for us to account for that pressure, then we introduce a constant A. We call this one the constant of a rare gas, or Van der Waals constant. So from ideal gas equation, where we had PV equals nRT, this pressure generated is as a result of the force of attraction being neglected. But in the case of rare gas, this pressure is less because the force of attraction is not neglected. So we are going to have P plus A on V squared. Then this volume and ideal gas from kinetic theory was neglected. Rare gases, from Van der Waals assumption, that volume shouldn't be neglected because we are considering the volume of the molecules, where the molecules is having definite shape and size. So we have V minus B equals nRT. So this A represents the constant of a rare gas, which accounts for the high pressure generated as a result of the collision between the molecules. And A on V squared, we call this one pressure defect, which accounts for the differences in pressure between rare gases and ideal gases. B, this constant B, is called the volume factor, which accounts for the effective volume of the molecules of a gas. So this is all about rare gas. So now let's look at the difference between ideal gas and rare gas. For ideal gas, they obey kinetic theory of gases and gas law. Rare gases do not obey gas law and the kinetic theory of gases. Then too, for ideal gas, the volume of the molecules of the gas is negligible as compared to the volume of the container. But in the case of rare gas, the volume is not negligible. Then the force of attraction on the ideal gas is neglected. But in the case of rare gas, the force of attraction is not neglected. Then under ideal gas, the kinetic theory said that the total energy depends on kinetic energy. But in the case of rare gas, the total energy is made up of kinetic energy and potential energy. And also said that the kinetic energy for ideal gas depends only on temperature. But in the case of rare gas, this kinetic energy is due to the constant motion of the molecules. And the potential difference is also as a result of the weak force of attraction between the molecules. Since the force is weak, the molecules are already distant apart, so they possess potential energy. So I would like you to consider these questions. Try your hands on these questions. We have 6 sets of questions here. So you apply the gas law and rare gases. We have equation of state of ideal gases and equation of state of rare gases. So let's look at the last question. 1 mole of a gas of volume 1.0 times 10 to the negative 3 meter cube at temperature 200 Kelvin has Van der Waals constant. So they've given us A, where they say I told you that it accounts for the high pressure as a result of the collision between the molecules. Then B is the volume factor, which accounts for the effective volume of the molecules. This is universal gas constant. So I find the pressure of the gas if the gas behaves as an ideal gas. Then I find the pressure of the gas if the gas behaves as rare gas. But don't forget, the pressure generated by rare gases is less than that of ideal gas, because for rare gases, the force of attraction is not negligible. We consider the force of attraction. So the molecule cannot move further away from each other, and they can't collide frequently against the walls of the container in order to generate high pressure there. Now let's go back to question 1. You see that the temperature is in degrees Celsius, but don't forget, under the gas law, we are considering absolute temperature, which means the temperature should be in Kelvin. So it's up to you to change the temperature from degrees Celsius to Kelvin before you can go ahead to solve. All the best.